All right. Is anybody on this list who hasn't shown me their passport yet? Do you have your passport? Can you fill it out real quick for me? Awesome. Thank you. Yeah, the health check. Yeah, thank you. All right. So for those of y'all who are not watching live and watching the recording, if you do see your name up here, don't worry. It is only relevant if you are coming on campus. But please do make sure that anytime you are coming on campus, your passport is up to date. I just realized I still have the background on, which is going to make it impossible for y'all to actually see me. 1 second here. All right, there we go. Cool. Your passport? Perfect. Awesome, thank you. Thank you, thank you, thank you. And I'm sorry, I know I should be getting to the point of the semester where I'm recognizing people's names and faces, but it's next to impossible. I don't know what it is about masks, but I see people who I've had in like 2 of my other classes that I don't recognize until they start talking. So it's also hard only having y'all 1/2 of the time, but I appreciate y'all putting up with that. All right, so while we're waiting on the last couple passports here, let's go ahead and get started. So today we're going to be covering Introduction to Hypothesis Testing. However, before we do, a couple quick things about the exam. The exam after the curve had a mean of 79.6%. Pre-curve was just about 70%. There were several students who, with this curve, got over 100%. However, I thought that the wording on some of the questions was a little confusing, and so I decided to make this curve a little bit bigger than it otherwise would have been, with curving to the top performer getting 100%. Don't anticipate that being on the case for future exams. And as I said in my email, whenever that was, days are starting to blur together. Whenever I said in my email, the second exam was a substantially harder exam for students last semester. So please make sure that you are studying extra for this exam. Now, one of the things I've done different this semester than last semester I taught this is I'm breaking up the content into 2 more exams rather than just the 1 more exam. So what will be on exam 2 is going to be less than what was on exam 2 for last semester. I think that was part of what was making it hard. But this content is really awesome. Awesome. Thank you all so much. Appreciate it. So I think that will help, but it is much more complex information, and it is going to be building off of concepts that seem to be giving the class as a whole a bigger problem for exam 1. So please make sure that you study up for that next exam. Here is the distribution. You can see it's negatively skewed here. These are just the raw scores, but gives you an idea of the overall performance. One question that vast majority of people missed on this exam was the one where I asked you to take the sum of squares and find the variance for that sum of squares, right? And so you had already calculated the sum of squares. The answer was 64.4. You knew that the sample had 10 people in it. We also knew it was a sample. How do you find the variance from this?
Sum of squares over n?
N minus 1.
Yes, n minus 1. So a vast majority of y'all did it just over n. But because it's a sample and not the population, it's n minus 1. All right? Now, it was constructed in such a way that if you did just divided by n and then took that variance to get the Standard deviation, you got full points for standard deviation. I wasn't trying to take off extra points if you screwed up an earlier step and had the consequence several steps later, but that will not necessarily be the case moving forward. So when it's a sample, it's divided by n minus 1. If it's a population, it's just divided by n. There also seem to be a handful of issues with looking up on the unit normal table that I provided. We'll be going over that a whole bunch more throughout the semester because this is just going to be kind of a recurring theme. It won't always be with the unit normal table. But that's something you're going to want to practice because that tripped up a lot of folks. Any questions about the exam? Concerns about the exam? I've got something in my eye here. I know it's not COVID approved to rub your eye, but nothing?
For the next exam, will we get to have like the cheat sheet and everything? Like you'll get to prepare the same way?
Yes.
Cool. Okay.
Yep. All right. Here's your fun fact of the day. Guinness estimates that 93,000 liters of beer are lost in facial hair each year alone. This is just making me feel better about the fact that I can't grow a beard. So, all right. Now, before we actually move on with the lecture, if you've ever had me in class before, you know one of the things I like to do about at the first exam time is ask for feedback, right? It's typically the case that we ask you all for feedback at the end of the semester, but that doesn't do y'all any good in my class. And so I do want feedback from y'all. So if you're online, go to Canvas. If you have your device here, you can go to Canvas. Or if you don't have your device, you can just fill it out on a piece of paper. But I want y'all to give me 3 things. Start, stop, and continue. So start are things that I'm not doing you want me to start doing in class. Stop, things that I am doing you don't want me to be doing in class anymore. And continue, things I am doing that you want me to continue doing in class. So take a couple minutes, fill that out. This will be for extra credit, and so put your name on it if you want that extra credit. If you want it to be anonymous, you can either leave your name off of it, although you can't do that on Canvas, or you can just email it to the staff assistant for psychology and ask it to be anonymized, and she can send it to me. But I think I've got tough skin, and I'm not going to hold it against you if you rail against me. So take a couple minutes, and I'll collect the pieces of paper. Take another 47 more seconds. All right, and if you're writing it down and you're done writing, I will take it from you. Need more time, take more time, but yes, ma'am. Cool. Thank you. All right, thank you all for the feedback. I will certainly try to incorporate what I can. It's not always going to be feasible, nor am I always going to think it's a good idea to change some of the things. If you wrote something completely unfeasible, like stop having exams, we won't do that. Every year I get some smart aleck who thinks that's the right answer. But I will certainly try to address any concerns you'll have, start doing things, stop doing things, or continue doing things. If there's a recurring theme that I notice that I feel like isn't appropriate for me to change the way I'm doing, I will certainly try to address why that's the case. But thank you all again for the feedback. Any just general questions about the class, concerns about the class so far in that feedback? This is kind of a good like check-in point. Cool. Cool, cool, cool. All right, so today we're talking about hypothesis testing. And in reality, we're going to be talking about hypothesis testing from here until the end of the semester. And with hypothesis testing, what we're trying to do is determine whether a specific treatment has an effect on a population. And when I say treatment, I can mean medical treatment, but it also just can mean any intervention. So it could be, is this vaccine effective against coronavirus? Or it could be, does texting negatively impact your ability to drive? Right? So treatment just means intervention. And we use a hypothesis to evaluate the results from a research study in which a sample is pulled from the population. So it could be the entirety of the globe's population, or the population could be UAH students. B, or two, the treatment is administered to the sample. The intervention is given. And then three, that sample is measured after that treatment. So if the individuals in the sample are noticeably different from the individuals in the original population, we can say we have evidence that the treatment has an effect. or the intervention did something. However, like I've said repeatedly up to this point, it's also the case that anytime you sample from a population, you're going to get slight differences, slight variations. If I collect the average height of people walking down the street, I may get 5'6", and then I may get 5'7", and then I could get 5'4", and then I could get 5'6.5". All right? You're just going to get slight variations. And so it could be the case that a difference you observe between the sample you selected and the known value of the population could be due just to sampling error. Right? Sampling error is referring to anything that could be motivating the that difference in the samples. And so just to kind of illustrate this point here, we have a known original population, right? This could be the population of everybody at UH. It could be the population of all 7 point some odd billion people in the world. And that population has a known mean. So in this completely arbitrary example, the mean for that known population is 80. From that population, we're pulling a sample, right? And what we're trying to infer is after we establish the treatment or the intervention, what is the ground truth of the new population over here, which is representing the entirety of the population that would be treated. Right? So if we want to see what are the long-term efficacies of the coronavirus vaccine, we may pull out 1,000 people who've gotten the vaccine, but that's not representative of all hundreds of thousands, millions, potentially billions of people who get the vaccine. We're just trying to infer to that treated population over here. And so the purpose of doing a hypothesis test is to decide between two explanations. One, that any difference between the sample and the population can be explained just from sampling error, just from those inherent differences you get. We would say there doesn't appear to be a treatment effect in this case. So perhaps the coronavirus vaccine, there's a difference between the rates of infection in those who get the vaccine and those who don't, but maybe it's just so small we can't say definitively that the vaccine actually did anything. The other explanation is that the difference between the sample mean and the population mean is too large to be explained just from that sampling error. We would say that there does appear to be a treatment effect. So in this case, the contagion rates of those, or excuse me, the infection rates of those who get the coronavirus vaccine is next to 0, and the infection rate for those who don't get the vaccine, let's say lifetime, is 50% or something. We would likely say that difference between those groups is too big just to be due to chance. Right? We'd expect little variations, but it's unlikely to be just due to sampling error. So the next logical question is, how do we know what that cutoff is? How do we know what's too big of a difference to just be due to chance? Well, we're going to be using a very similar approach to what we were doing with the z-scores, right? And so this distribution here represents the population. You have this representation down here of H0. We're going to call that the null hypothesis, and we'll cover that more in just a second, but just kind of ignore that component. But we know within this population distribution, because the height of this distribution at any given point is representative of the frequency, we know that it's very likely to get something kind of in the middle here. And it's very unlikely to get things out in the tails, right? These tail areas are low probability events. It still could happen. You could get a sample mean that is in fact out here in the tail. But it's very unlikely given that population.
Your Zoomies can't hear you if you can hear me. I don't think he can hear me.
Probably can't hear us.
Nope.
I'm assuming the video froze.
Well, the video's fine.
No, it's not. Never mind. I had it on small screen.
You know that.
I guess class is over.
Good one.
Imagine he can hear us and so can the whole class.
Oh, that's even better, right?
That'd be amazing, yeah.
Think.
Whoops.
Think.
Honestly, he's a beast for doing all this at the same time.
Yeah, for real. I can't imagine.
Yeah.
He's doing it well.
Yeah.
He's
Definitely
the
the
best
best
one of all my teachers.
Definitely the best class I have right now.
Yeah, me too.
Other people are struggling,
Yeah.
like other professors.
It's because no one knows how to use their computers.
I mean, he's doing great last semester too. He immediately adapted.
Oh, that's good.
Give him a promotion of some sort where he gets to be the director of all of the everybody's stuff.
The
That's the
reload.
one. That's the
Can you
one.
hear me now?
Yes.
Yeah.
we can hear you.
Hey.
Could you hear us?
I could not hear you.
Oh, okay.
I
okay.
assume you were all
Probably good.
sharing your enjoyments about the class. So,
Yeah, we were.
They were looking for extra credit.
bullshit. Sorry. Yes. No. I don't know why. Every once in a while, the Wi-Fi decides to kick me off, but it does. So, thank y'all for making hay about it in the chat box. Sorry about that. All right. So, just to reiterate, what probably was the last thing that y'all missed. Again, we're talking about the events represented in these tails that are really unlikely events to occur. Right? So based off of the probability distribution of selecting a sample in the tails here and there, we know that if we do get a sample that has a value in these extreme scores, it could be due to chance, but it's very unlikely to be due to chance and likely has some other external explanation.
Okay, so within the majority means that it is due to chance, and outside of it means it's not due to chance, right? That's all right.
It's not necessarily the case that it does mean or it doesn't mean, but we're
Okay.
using kind of the weighting of probability. So if we pull a sample that falls somewhere in here, the probability is such that we can't definitively say, or we can't say with all that much certainty, that that's an unlikely event, right? So if you flip the coin 1,000 times, it may come up heads 501 times, but you know just kind of intuitively that that's a high probability event, right? It's very likely to be in this case. But when you get to the extremes, you're saying this is such a low probability event that there has to have been some sort of effect there, right? If you sample basketball players in the NBA, their average height is probably going to be close to what, 6.5 feet tall? And you know that's such a low probability event that you would sample a group of people who are 6.5 feet tall, that there has to be sort of outside influence on that fact. Does that make sense?
Yes. So it's kind of like whether or not it's a coincidence, kind of.
Yeah, that's a good way to think about it. Yeah, Sonny. It totally depends, right? And so we'll go over some examples that I think will help make this concrete. But let's again go to the coronavirus vaccine, right? And let's say we had a reduction in infection rate that was a really low probability event just by chance, right? Let's say, based off of our calculation, there is a 1% chance that we would have sampled at that value given our known population. In that case, we can say that because that's such a low probability event of sampling just out of that population, it's likely the case that because that group got a vaccine, that vaccine was effective. And so whether you're in the tail or the body kind of depends on what the conclusion is you're trying to reach. Does that make sense? Cool. So we'll do some concrete examples that I think will help solidify that. All right, so we're going to use 4 different steps in the process of hypothesis testing, and some of it's going to be new terminology. So step 1, we're going to state the hypotheses and select an alpha level. All right, this thing over here that looks like a fish, we call that our alpha. And so our null hypothesis, or abbreviated H0 or H0, always states that the treatment has no effect, no change, no difference, etc. So if I want to see if texting has a negative impact on driving, the null hypothesis would be that texting has no effect on driving. And we'll go over the alternative hypothesis in just a minute. The alpha level is going to be the critical region. And we'll go over this more in depth in a minute. And it's also going to set the type 1 error rate. And type 1 error rate, as you'll see in just a couple minutes, is the false positive rate. So what is the value at which I'm willing to say, okay, every so often we're going to get a false positive? So let's say I pick an alpha level of 0.05. That's a probability. That's essentially saying that if I test 20 coronavirus vaccines and none of them are truly effective, 1 out of those 20 is likely to come back as effective. Right? That's a false positive. So again, the critical region is consisting of outcomes that are very unlikely to occur if that null hypothesis is true. If there's really no effect of texting on driving, finding a difference should be very unlikely. That is, the critical region is defined by sample means that are almost impossible to obtain if the treatment has no effect. And when I say almost impossible, that means that these samples have a probability that is less than that alpha level. All right, so let's put some concrete values to this. Let's say I was only going to say that the coronavirus vaccine was effective if and only if the value it gave me had less than a 5% chance of being the sample from that population. And so let's say that we've set our alpha level at that 0.05 or that 5%. That means I'm going to split that 5% into the two tails such that each tail has 2.5%. And then I'm going to look at the infection rates for those who got that vaccine. And if that value is more extreme in this direction, we'll say it had an effect. If it's, or it had a positive effect. If it's more extreme in this left direction, we'll say it actually had a negative effect. It actually made you more susceptible to catching the virus. And this actually happens with vaccines, right? There are some vaccines that actually make you more susceptible to the virus. It's rare, and that's why we go through testing. But we want to know that as well, right? And so now we can say, we've sampled a group, we've given them the vaccine, we know what their infection rates are, and we can now put it on this curve. And let's say the sample infection rate is up here. We can say, based off of our two-tailed test here, with that alpha level of 0.05, or 2.5% in each tail, that the probability of getting that sample, if the vaccine did not have an effect, would be so low as to make it almost impossible. So if we get any value in the tails and the extremes out here, we say we reject the null hypothesis. So in this case, the null hypothesis would have been that the coronavirus vaccine has no effect. Well, because our sample right here was more extreme than these criterion values here, we can say we're rejecting that null hypothesis. The coronavirus vaccine did have an effect on infection rates. Yes. Yes, if it's on kind of to the extreme, if it's in the tail beyond what that criterion value is. So if it's further to the right than this criterion value, you reject the null. If it's further to the left than this criterion value, you reject the null. That make sense? Cool. Yes? So do you mean whether it helps or hurts? Yes. And so we'll get into some concrete examples that I think will help explain that. But it'll be clear as you set up your actual statistical testing what that direction means. Okay, this is a good question, very good question. So step 3 is then computing that test statistic. Right, so we know what we want our alpha level to be, and it's typically the case that it's 0.05. We know what our null hypothesis is. We've gathered our sample. And now we're calculating our test statistic. And this is the step that's going to be changing for the rest of the semester. In this chapter, we're looking at the z-scores. However, in every other test we're going to be covering this semester, the test statistic is forming a ratio comparing the obtained difference between the sample and the hypothesized population mean, or the known population mean, versus the amount of difference we would expect without any treatment effect. Right? And this is where that standard error comes in. What's the amount of variation we can reasonably expect if the treatment had no effect? And so this is, again, just reiterating what I showed you on that graph a few slides ago. If the value of that statistic is large enough to be in that critical region, in those tails, we conclude that that difference is significant. And in this case, we mean significant in the statistical sense, not in the colloquial sense. When we say significant, we don't mean meaningful. We mean that it has exceeded our alpha cutoff. There's a statistically significant difference. And in this case, we're going to reject that null hypothesis. So if the mean difference is relatively small, then that test statistic will also be low or small. And if that happens, we conclude that the evidence from the sample is not sufficient to reject the null hypothesis, And so we say we fail to reject the null hypothesis. All right, so let's say I am testing whether texting has an effect on your ability to drive, and I find that it does have an effect on your ability to drive. Do we reject the null hypothesis or fail to reject the null hypothesis?
Reject.
We reject the null hypothesis, exactly. Because that null hypothesis is that there would be no effect. So we're rejecting that because we found it does have an effect. Come on.
You're not recording now? Oh, there you go.
Thank you. There would have been potentially 2 chances for extra credit. Although this is profoundly annoying. All right, cool. So, get everything back set up here. All right. Amber says, where do you get the alpha level? So the alpha level is something you establish ahead of time, right? And so we're going to go over type 1 and type 2 errors to discuss where you get that in just a second. But the standard alpha level is 0.05. That's typically what we use for testing. So just because the sample mean following that treatment is different from the original population mean does not necessarily indicate that that treatment has caused change. Like we've already talked about, it could just be sampling error. However, we can also have kind of this classification of 2 different types of errors, right? And so a type 1 error occurs when the sample data appear to show a treatment effect, when in fact there is no treatment effect. The hypothesis test is structured in such a way that type 1 errors are very unlikely, specifically that the probability of a type 1 error is equal to that alpha level. And so, Amber, you asked, how do we set our alpha level, or how do we pick our alpha level? And it's based off of kind of an a priori or a beforehand calculation of what do we want our type 1 error rate to be. In some cases, we may want to prefer a type 1 error to a type 2 error. And we'll go over that in just a second, weighing in. But if we set our alpha level at 0.05, that means that more or less what it's supposed to mean, it doesn't actually work out this way, but what it's supposed to mean is that 1 out of every 20 times we find a significant result, that's not a real result. It's just due to chance. A type 2 error occurs when the sample does not appear to have been affected by the treatment, when in fact the treatment does have an effect. So in this case, you as the researcher would fail to reject the null, even though there would be an effect. Type 2 errors are most likely to occur as a result of a very small treatment effect. Technology is revolting here. And so, an easy way to remember this, we have type 1, we have type 2. Type 1, just turn into a P, false positive. Type 2, turn into an N, false negative, right? Pretty straightforward. And so we can break this down, break down this decision criterion into a 2x2 matrix, right? In one case, we would say that the actual real ground truth, whether we realize it or not, is that there's no effect, right? That the vaccine doesn't actually help. The other one would be that the ground truth is that the vaccine really does help, whether or not we are able to realize that. And then on the left-hand side is the experimental decision, right? So if we reject the null hypothesis, when we should have actually retained the null hypothesis, that's our false positive, our type 1 error. When we reject the null hypothesis, and we should, in fact, reject the null hypothesis, that's a correct decision. When we retain the null hypothesis, and we should, in fact, retain the null hypothesis, that's another correct decision. And when we retain the null hypothesis or fail to reject the null hypothesis, when we should have rejected the null hypothesis, that's a type 2 error. And so let's go over an actual example here. So a researcher would like to assess the quote-unquote miraculous claims of improvement made in a TV advertisement about a phonetic reading instruction package. It's known that the scores on standardized reading tests for 9-year-olds on a normal distribution with a mean of 45 and a standard deviation of 10, a random sample of 25 8-year-olds are given the reading package for a year, and the manufacturer's instructions are followed by their parents. At age 9, this sample is given the standardized reading test. The mean score for the sample is 48.6. Test at an alpha level of 0.05 in 2 tails. And so, what is this saying? This is saying that we know the population has a reading score on average of 45 with a standard deviation of 10. And our sample that got this phonetic reading package, whatever we call it, had a sample of 48.6. Is this sufficient to say that this reading package helped the students? Step 1, we have to define our hypotheses, right? The null hypothesis is that mean 1 equals mean 2, or the mean for the sample equals the mean for the population. And this is not an exact equivalence, but this means statistically equal, right? This is the null hypothesis, that there's no statistical probabilistic evidence that we should reject the null hypothesis. The alternate hypothesis, the research hypothesis, H1, says that these are not the same. That the population mean does not equal the sample mean. Now, one of the things you notice is if we go back here, they don't equal, right? And so you may be inclined to say, yes, reject the null hypothesis. But again, what we're doing is looking at probabilistically, are these equal? Not are they, in fact, exactly equal? Step 2, we're going to set that criterion, right? So this should be an alpha, not an omega. There we go. So our alpha level is 0.05, and we're going to do it in 2 tails, right? You could do it in just 1 tail if you've got a direction to expect, but it's typically the case that you do 2 tails. And so 2 tails means we're going to take that alpha of 0.05, that probability of 0.05 or 5%, and split it up into those 2 tails. So now we need 0.025 in each tail. So if we go and look at the unit normal table we have over here, let's look for 0.025. And we go all the way down here, right above that line, right? That's in the tail. So 1.96 is our value. Oops. So 1.96 is our critical cutoff value. If we think about the distribution again, we've said at positive 1.96 and negative 1.96 are our criterion cutoffs. If our z-score that we calculate is greater than positive 1.96 or less than negative 1.96, we're going to reject the null hypothesis. Otherwise, if it's in the middle here, we're going to retain that null hypothesis. We're now going to calculate the statistic using the equation we've used before for z-score. So we're going to take our mean from our sample minus the population mean divided by the standard error. Right? Find the standard error. We take the standard deviation of the population divided by the square root of that sample size. So we know that our population has a standard deviation of 10. And we know we have sampled 25 students. So 10 divided by the square root of 25, or 10 divided by 5, gives us 2. And now we can plug all that in. So our 48.6 is the mean for that sample, for the group that got that reading tool, minus 45, which is that population mean without the reading tool, divided by 2 gives us 3.6 divided by 2, or 1.8. So we had our cutoffs at negative 1.96, positive 1.96, and our actual value for our sample came in at 1.8. So we failed to reject the null hypothesis, or we retain the null hypothesis in this case. So even though there was a 3.5-point difference, we're saying that that is not sufficiently big to lead us to believe that this actually had an effect. Questions about that? Awesome. So now you all can go home. Not yet, we still have more class. Oh, does somebody have a question? Nope, okay. So now you can test against things that you know. You have known population values, right? So if you want to see whether or not it's true, yes, exactly, Kenya. And you want to see whether or not it's true if playing Baby Einstein for your baby, in fact, makes your baby smarter, you can go and test it. You know what the IQ is, the standard deviation, the mean for IQ, and now you can compare what a sample of babies who got Baby Einstein IQ is compared to that. And so this was a case of a non-directional test. We wanted to know whether or not, or we wanted to know whether the that reading package helped or hurt reading, right? So going back to the vaccine example, we want to
Someone
know
has
whether.
a question
Yep.
in the chat. Someone said I have
Oh,
a
okay.
question.
Yeah. Kate, what's up? How could you tell it was significant? Because we were comparing it against these critical cutoff values. So because the 1.8 we found was not to the right of positive 1.96 and was not to the left of negative 1.96, we say it was non-significant. Does that make sense? Good, cool. All right, so yeah, the example of the flu vaccine. We want to know, not only is it just effective, we want to know potentially is it hurting, right? So the early test of a vaccine, you want to know not only is it going to help prevent against infection, we also want to know if it's going to make you more likely to become infected. Because if so, we don't want to do that either. But there are also times where we have a reason to believe, based off of prior data, that the effect is going to be directional. Right? We've got reason to believe that it can only affect in one way and not the other way. So you're predicting in a specific direction, either increasing or decreasing. It's possible to incorporate the directional prediction into the hypothesis test. We call that a directional test or a one-tailed test because we're using only one of those tails. So an example of this would be if the original population has a mean of 80 and the treatment is predicted to increase the scores, then the null hypothesis would be that the mean is less than or equal to 80. Or said another way, the null hypothesis is that there is no increase. And in this case, the entire critical region would be on the right-hand side. Because we think that whatever intervention we have, whatever treatment we have, is only going to have, a positive effect. So here, let's work out another example. Patients recovering from major operations normally spend an average of 6.3 days in the hospital. The distribution is normal with a standard deviation of 1.2 days. The hospital is trying a new recovery program, and the first 10 patients were released in an average of 5.5 days. On the basis of these data, what can the hospital conclude about the new recovery program? Test at the 0.05 level, so that's our alpha level, with one tail. So we've set our hypotheses such that the null hypothesis is that the sample is going to be less than or equal to the population. That should be H1. And the alternative hypothesis is that that sample, actually, let me rephrase this. So we are, because we're looking at time decreases, it's actually flipped, right? And so we are expecting that the null hypothesis is such that the sample here is greater than or equal to that population. The alternative hypothesis is that the sample we collected after that new treatment intervention is actually going to have less days than that population. And so we're taking our, once again, this should be alpha. We're taking our alpha level of 0.05, and this time we're going to put all of that into just one tail, right? We don't need to split it up into the two tails. So now we're going to look at what is the z-score, the z-critical value that corresponds to the alpha of 0.05. Right? So we go proportion in the tail, column C, until we get down here. You can see that 0.0505, 0.0495, we're going to take the more extreme of those. So that z-critical value is going to be that 1.65. And because of the directionality of it, we're going to set that to be negative, right? Because we're expecting that this treatment intervention is going to have them have less days spent in the hospital. So we're going to calculate the statistic. Again, it's going to be the sample mean minus the population mean over the standard error. Standard error is going to be the standard deviation divided by the square root of n. And so our 1.2 day standard deviation for the population divided by the square root of 10 for our population is, that should be 1.38, I think, through and through. Yeah. All right. Man, this slide shows all sorts of riddled with mistakes. My apologies. All right. So the z-score is going to be what is our sample mean minus the population mean. So 5.5 days minus 6.2 days divided by that standard error, or that 1.38. That gives us a z-score of negative 1.84. Because negative 1.84 is more extreme than the negative 1.65, so let's go ahead and draw this here. It's negative 1.65. Because negative 1.84 is more extreme, further into the tail, we're going to reject the null hypothesis. And in this case, what that means is that we can say the new recovery program does, in fact, have a significant effect on the length of time that somebody stays in the hospital. Or more precisely, that new treatment significantly reduces the amount of time that a patient has to stay in the hospital. Now, I said at the very beginning, when we were going over all this significance, that significance means statistically significant, meaning that there is a statistical difference, and not that it's a meaningful difference. The degree of how much kind of meaning you can attribute to an effect is measured by what we call the effect size. Right, so the hypothesis test is influenced not only by the size of the treatment effect, but also things like the sample size. And so if you get a big enough sample size, you're going to be able to find significant differences between any groups. Thus, even a very small effect can be significant if it's observed in a very large sample. And so you will see this all the time. So, thank you, Jace. All right, so that was supposed to be 0.38 on the back there. All right. And so, you're going to see this all the time in real-world examples where you'll see a write-up that says, eat more cashews and you'll live longer. Well, it could be that eating a handful of cashews every day makes you live an extra 6 years. Or the effect could be really small, such that you need to eat a pound of cashews every day to live 15 minutes longer. Right? The first case, that was kind of a meaningful effect. Yeah, I want to live 6 years longer, and just a handful of cashews, definitely worth it. The second is not a meaningful effect. You're telling me I have to eat a full pound of cashews every day, and I only live 15 minutes longer? Not worth it. Right? So that's what we're talking about when it comes to the actual effect sizes. We typically use what's known as Cohen's d to measure that effect size. And Cohen's d is nice because it is just about as easy as they come, such that it is the ratio between the mean difference and the standard deviation. So a Cohen's d of 1 means that the sample is 1 standard deviation above the mean. So if the baby Einstein videos have a Cohen's d effect size of 1, that means on average, they're taking your baby from 100 IQ to 115 IQ. And so this allows you to see not only is it a significant effect, but is it a meaningful effect? How much longer am I going to live if I eat a handful of cashews? I don't know why I always pick on cashews when I do this, but they're a garbage nut. And finally, we're running kind of out of time here. The power of a hypothesis test is defined as the probability that that test will reject the null hypothesis when the treatment does have an effect. The power of a test depends on a variety of factors, including the size of the treatment effect and the size of the sample. And so one thing you'll hear a lot in scientific discussions is that test was overpowered. If a test is overpowered, you're likely to find a significant effect when there is no real effect. If it's underpowered, you're likely to find no effect when there is a real effect. And so just kind of conceptually as the last thing we're going to do today, looking at this, you have your population distribution, you have your sample distribution, you have set your z-score for 1.96, and what you can see here is that the mean differences between these two groups are large. And you can see that the mean is going to fall to the extreme of that criterion, that reject the null hypothesis. And so the bigger this gap is, keeping the variance the same, the bigger that effect size is going to be. Keeping that distance the same and shrinking the variance, what we have here, is going to increase the effect size as well. Questions about what we covered today?
About when we have there's a directional distribution, and it's the null hypothesis. It's the mean is less than or equal to or is it the population mean is less than or equal to the sample mean?
Yeah, so I mean, it depends on what your directionality hypothesis is. If we wanted to see whether eating McDonald's every day was going to make you heavier, it's likely not going to make you lighter, right? So that would be the directionality. And in that case, our null hypothesis would be that the population mean is greater than or equal to the sample mean. Our alternative hypothesis, or a research hypothesis, is that that sample mean is going to have a weight greater than that population mean. Does that make sense?
Yeah, so we pretty much base it off of what our statistic is actually looking for.
Yes, exactly.
Okay. Okay. But it's population versus sample when we are looking at those two different means, right?
Exactly. Yep.
Okay.
Other questions? You said go over this again? So all this is saying is you have your population distribution over here. You have your sample distribution over here on the right-hand side, right? And so what we can say is that there is a significant effect because that mean value, when divided by the standard error that we would expect from this variance, this is becoming a really busy slide here, is to the extreme of where that z-score is, right? And so because there's not a lot of overlap between these two distributions, we say that this would be representative of a significant mean. Does that make sense? Okay. All right. So that's all we have time for today. I've even run a little bit over. If you do have questions about this, set up a meeting with me because this is going to be crucial for you to understand with everything as we move forward. And yeah, I'll stick around if you all have any questions. Otherwise, I will see you next time. And thanks for bearing with the technology issues and my own stupidity.